Jnanam paramam dheyam. Knowledge is supreme.
Now, we move on to our next topic. So far, we have discussed frequency domain spectroscopy. Now, we are going to talk about time domain spectroscopy. Okay, can we begin? Can we begin our discussion now? Right. So, what is the idea here? The idea is this: the spectrum that we are familiar with always is something on the y-axis. Let me write power today against some measure of energy, let us say wave number, right? And for an ideal spectrum, it is going to be, let us say, one line. Of course, if all the spectra in the universe were single lines, it would have been a very precise, but an absolutely boring situation. Thank God that not all spectra are single lines. Okay? But to understand, let us start with this. Single line here, what kind of light does it imply? One type. So, what do you call it? In a little monochromatic. So, the way I draw it here, I indicate a monochromatic radiation, right? Single wavelength, single energy. Now, if I want to represent this in time domain, an equivalent representation when x axis is time, what would it be? Let me call this power in nu bar domain. This I can call power in time domain. What will it be? It will be an oscillating electric field, right? Yeah? It won't be same power. Okay, let me say this is E. What is electromagnetic radiation? An oscillating electric field, right? This is not electric field, this is just the intensity. So, oscillating electric field, you can say it's either a sine wave or a cos wave, whatever you want to write. Let me draw it as a cos wave. Something like this, a single sine or a single cos wave, okay. They are equivalent to each other, is that right? I can draw it either like this or like this. So, when I acquire the data, I can also try to acquire either like this or like this. How we acquire like this, we will see. But can there be any advantage of the time domain measurement? What would the advantages be of time domain measurement if we can do it? First of all, how do you make a frequency domain measurement? You measure one frequency at a time. If I want to measure it in time domain, how will I measure it? But anyway, before going there, I think I want to show you something else. This is what I have drawn on the board as well, right? This is a representation of a monochromatic radiation. Let us say I don't have monochromatic radiation. I have two. This is what it looks like. You see what happened? When I have monochromatic radiation, then I have a regular sine wave or a cos wave. If I add another frequency to it, what happens is the shape changes, not a regular cos wave that we know. Okay. Why does this plot look like this? Sorry? Superposition of waves. So, right. So, let us go step by step. Then it is right. In some regions they cancel, in some regions they reinforce. I have drawn cos waves, right. So, for x equal to 0, the value is 1. So, when values are 1, it does not matter on the frequency, right. For x equal to 0, no matter what frequency it is, the values are 1. That means the waves are in step, they are in coherence, right. What happens when you go to any time greater than or less than 0? Frequencies are different, right. So, they now start getting out of step. As they start getting out of step, what will happen is they do not reinforce each other to that extent, and there will come a situation where they will completely cancel each other, destructive interference, right. Because of this, you get a pattern like this. This has a name. What is this called? This kind of a pattern is seen in interferograms. Okay. If I mix more waves, then what will happen? First of all, I have to zoom out a little bit. This is what happens. At time 0, they reinforce each other, they have added more waves, but then they get out of step faster. Have we understood this? If not, please ask now. Like think of two people running around Gymkhana ground. Okay? Let us say I run a race with Akansha, right? What will happen? We will start from the same point, then we are in phase. But then Akansha is an athlete, I am not. So, she is going to go much further. So, some path difference will come in. Very soon, if we keep running for long enough, you will see I am at one end of the field, Akansha is on the other end of the field. So, if we were waves, then the situation would be something like this. So, this is me. This is Akansha. Okay. So, at this point, we are more or less on the opposite, diametrically opposite points of the field, right. Here you get, if you are waves, you get complete destructive interference. So, you will get a 0 here. Then what happens? Then you start getting back in phase, right. Two people running in the same direction, but at different speeds. So, when they are diametrically opposite, then the difference is maximum. When they keep running, what will happen is the faster runner will start catching up with the slower runner, right. That is what happens, say here. Here see, you have one maximum close to another maximum here. There again the value will be large. The moment the value becomes large, after that what happens? Again this phase difference starts building. So, you develop what is called, if you remember your lessons in sound in physics, you start getting a beating pattern, right, you get beats. Okay. What happens if the two runners, I find it easiest to understand thinking of runners, these two runners, if they run at very different speeds, then what will happen? Suppose one person is not running, I am tired, stand, Akansha runs 200 laps, then what will happen? She will keep catching up with me at regular interval. But suppose I can run at more or less the same speed as her, then what will happen? It is not so easy for her to catch up with me, right. So, what kind of beating frequency you will get depends on the relative speeds or relative frequencies of these two waves. If they are very close, then frequencies are small. If they are very far apart from each other, then frequencies are large, right. So, this is what happens when you mix waves. So, you can understand now, instead of this easy diagram that I have drawn, if the intensity is actually something like this, many frequencies are there, what kind of time domain signal will I get? I do not have to follow the sequence, and not everything will have the same amplitude also. Can I do what? Yes. See, what is the difference between cos and sine? Just phase difference, nothing else. Okay. So, you get this signal like this. At first look, it does not look like signal at all, it actually looks like noise, but that is your signal. And there is one important thing to understand here, and that is, let us take this point in time. This point in time, does it have information of this frequency or this frequency or this frequency? Yeah, Just be brave. I mean, what you're thinking is right. I choose any arbitrary point on my interferogram, time domain signal. Does it have contribution from this frequency or this frequency or this frequency? All, naturally, all, right? And think of the other way around, any point here that has contributions from all the waves, right? Actually, sorry, from all the time points, isn't it? So, these two are completely related to each other. So, if you have frequency domain spectrum, you can actually generate the time domain spectrum. That is what I did, isn't it? So, what I have done here, what I have written here in this line is essentially spectral information. I have said that I have something that has a frequency of say 10, something that is 11, 12, so on and so forth. I have just mixed. So, this is the way in which you can generate the time domain information if you have frequency domain information, and there must be some way of going the other way as well, right? And the way you do it, I think you know already, is by Fourier transformation. Fourier transformation is the translator between frequency domain and time domain data, right? How it comes, we will slowly come to that also. Is there any question about this so far? This is something we will come back to once again when we talk about NMR. So, it is important that we understand this here. Have we all understood what time domain data looks like, right? Now I can come to the advantages. Is there any question? If there is a question, please ask now. No question? Arun? Sure? Okay. So, now see, if you look at this and that, the first advantage becomes obvious. How do you pronounce this word? Name? Huh? Jacquinot. I have no idea why that T is there, but what can I do? That was his name. Jacquinot. Jacquinot advantage or throughput advantage. See here, when you do frequency domain measurement, as we discussed, you have to measure frequency by frequency, one point at a time. Here, when you do time domain measurement, all the colors are going in at the same time, alright. You are generating interferogram, that is all. Have I been able to make the point, right? The entire light goes in. So, if the entire light goes in, naturally signal intensity is large. So, signal to noise ratio will also be better. We just discussed that if signal is large, then signal to noise ratio becomes better. Now, see, you measure say from 500 to 5000 centimeter inverse in steps of say 3 centimeter inverse. How many points would that be? 1500. So, you have to measure this 1500 points one by one, right. Now, all the intensity that you collect in this is going in at the same time when you do a time domain measurement, because you are not using a monochromator, right. When I do, we will see very soon how the time domain measurement is actually done, but schematically you can think like this. This is your source. Again, when I say source, it can be the light source or it can be an emissive sample, or it can be the light from the light source after passing through sample transmission. That just goes into your detector, which is capable of producing a time domain output. How it produces time domain output is a different question, of course. Okay. If I do this, is there any need of putting in a monochromator here? No, right? Because which frequencies are there is something that I am going to learn when I do a Fourier transformation of that. No monochromator. So, the entire light goes through, throughput is high. Okay. That automatically makes the signal to noise ratio significantly better than what it would have been if you collected frequency by frequency by frequency. Have we been able to understand this? If there is a question, please ask. So, first is Jacquinot advantage. Second is resolution. You can actually get a very highly resolved data. How you can control the resolution is something that we are going to discuss in a few minutes. Okay, but just believe me on this for now, that you get a good resolution. And third is you are doing this multiplex detection. When you do multiplex detection, signal to noise ratio becomes better anyway. These are the advantages. But of course, as we have now understood, there is no free lunch in the world. It cannot be advantages all the way. There is a problem as well. Multiplex detection means you are measuring all wavelengths together. So once you do that, that signal to noise ratio, remember the discussion we had, that comes into play. Now, what is the problem? The problem is this. This is what we want to do, isn't it? I want a detector and I want the detector to give me time domain information. How do I get time domain information? What is the device? Now, this is something we have studied in 11-12 modern physics. So, you have to tell me. If I want to observe a signal that oscillates in time, what is it that I use? I have some photodetector that collects it, but then what is it that lets me see that signal? Some signal that changes with time. If we cannot say, we will take help from the in-house physicist, but yeah. Now AC, to theek hai, but AC is a current. Suppose I have a signal, I have some light whose amplitude or I have a field which oscillates with time. What is it that I use to see this signal? If I tell you the answer, you will of course regret because you know already. Vishnu? No? Okay, tell us. Yes, of course I am referring to the oscilloscope. Oscilloscope. Ever heard of oscilloscope? No? Achha, ever seen an oscilloscope? Where? Dur Baba, outside your lab. See, you people are not 10-year-olds. So, I will not believe it if you say that you have never seen a good old fashioned TV. So, the big fat TV, remember, what does it have? It has an electron tube, electron gun, which sends a beam of electrons, and then you have two plates like this and you have two plates like this. So, apply a field here, then the electron beam deviates this way or this way. Apply this field, vertical field, electron beam moves up and down. So, in an oscilloscope or in a television set, what we have is this. We have an electron gun which sends a nicely collimated beam of electrons, okay, and you have a phosphor screen. So, the electron beam goes and hits the screen and you see a spot. Now, maybe I will draw it instead of acting out. This is your electron beam. Now, what you have is you have two plates, one like this. Let us say this is plus, this is minus, high voltage of course. So, that is why you are not supposed to open an old fashioned TV, right, because at 10,000 volt potential difference is there, you do not want to touch it. And another set of plates is like this. Let us say this is plus, this is minus, okay. So, this is one set, this is another set. What happens if I apply a high potential difference here? Let us say this plate is minus, this plate is plus. Then the beam will deviate this way, right. Now, if that's all I do, then let us say this is the screen, the beam is going to hit here and you will see a glowing spot here, right. I have to draw a two-dimensional screen also. If I apply a potential difference between these two, then what will happen? Say this is plus, this is minus, then the beam will deviate like this, right. And now, there will be, alright. So, by applying some voltage on this horizontal plate, you can make the electron beam move along a horizontal plane. By applying a signal on the vertical plates, potential difference on vertical plates, you can make it move up and down, right. That is how an oscilloscope works, okay. So, on the horizontal plate, you apply what is called the trigger signal, which moves it at a regular interval, that gives you the timing information. In the vertical plate, you provide the signal, let us say an oscillatory signal, that moves it up and down. So, on the screen of the oscilloscope, you can see signals like this. Okay. But the problem is this. Let us say we want to do a measurement of some IR frequency. Let us take a typical IR frequency, 1000 centimeter inverse. If this is the wave number 1000 centimeter inverse, what is the wavelength, or say what is the frequency nu? Nu will be C divided by nu bar or multiplied by nu bar? So, lambda nu equal to C. So, nu by nu bar equal to C. So, nu equal to nu bar into C. Is that right or wrong? Right? So, if nu bar is 10 to the power 3 centimeter inverse, C is 10 to the power in centimeter per second, what will it be? 10 centimeter inverse. So, frequency is going to be 10 to the power 3 centimeter inverse. If frequency is 10 to the power 13 centimeter inverse. If frequency is 10 to the power 13 centimeter inverse, what is the time period? Yeah? I forgot the 3. Is 3.3 picosecond, isn't it? Is that right? 1 by 3 into 10 to the power minus 13, that comes to 3.3 10 to the power minus 12. So, the problem is oscilloscopes are not that fast. It is not possible for you to see 3.3 picosecond kind of signal directly on an oscilloscope, alright. So, we need a way out, and the way out is frequency modulation. That is what we will discuss in the next period.